Hey guys, and welcome to the YouTube review. I'm sorry it's been so long. We've had a lot of technical difficulties. Unfortunately, I tried to do one last week, and YouTube rejected it and deleted it from my computer. And I figured it would be best to take a breather, redo it before chunking my computer out the window. Well, I don't have windows here, so into the wall. So, we went over Chapter 3, and so I'm going to talk a little bit about Chapter 3, review Chapter 4 just a tiny little bit, and I'll post another one for Chapter 4 this week. But, Chapter 3, we went over a couple of really big concepts in Chapter 3. The first of which being the mole. Okay, the mole is a very, very important thing in chemistry. And we talked about the mole, and I described it as being the chemist's dozen. Okay, you can have a dozen donuts, you can have a dozen pencils, and a dozen desks, whatever it is. But no matter what it is, you have 12 of that unit. Okay, so it can be 12 coffee cups, but you have a dozen no matter what thing it is. Okay, so no matter if you have 12 lamps, 12 coffee cups, or 12 jugs of water, okay, it's all a dozen of those things. Now the mole is a lot like that. It's called the collection term. Except for instead of 12, like a dozen, it's 6.02 times 10 to the 23rd. Okay, it's a huge number. Now, what we call that is Avogadro's number. He's the dude who came up with it. And the other thing we went over before we talk about moles is molar mass. Okay, we talked about molecular weight and formula weight being the masses from the periodic table added together, all those atomic masses, for a molecule. And if we report that in grams, so for water, okay, we go to the periodic table, we see hydrogen is 1 and oxygen is 16. So we have 2 hydrogens, so that's 2 1s and a 16. So 18 atomic mass units is the molecular weight of water. And 18 grams per mole is the molar mass for water. Okay, so it's very important to make that distinction. And molar mass is something that you should be automatic, a knee-jerk reaction. You see mass and you see moles, you have to go and find the molar mass of that substance. Okay, that should be a knee-jerk reaction. You shouldn't need any direction on that. If you see moles and you see mass, anywhere there, you have to convert from mass to moles. You have to go to the periodic table. Don't throw in Avogadro's number or anything wonky. Just go to the periodic table, add up the atomic masses, and you'll get your molar mass. Now, when we're converting, we talked about Avogadro's number. If you're converting from atoms to moles, okay, we said 6.02 times 10 to the 23rd. We're converting from atoms to moles. What we're going to do is we're going to divide by Avogadro's number. Okay? Now, let's look that in the real world. So if we've got a dozen, if we've got 24 donuts, we want to know how many dozen that is. Okay, we take 24 divided by the number of units in a dozen, which is 12. And that'll give us 2 dozen. It's the same thing with moles. Okay, if we've got 3.01 times 10 to the 23rd atoms, we're going to divide by Avogadro's number, just like we divided by 12. Okay, it's in units in a mole. Okay, so we divide by Avogadro's number, and we'll get half of a mole. Okay, so from atoms to moles, you divide by 6.02 times 10 to the 23rd. From moles to atoms. Okay, if you can't see this, that's okay, I'm talking about it. So from moles to atoms, what we do is we multiply by Avogadro's number. So we take the number of moles, multiply by Avogadro's number, and we get the number of atoms. Just like if we had that same 2 dozen, and we had 2 dozen donuts, and we wanted to know how many donuts that was, we take 2 times 12, which is the number of units in a dozen, we'll get that 24 original donuts. Now it's very important that you understand what this is. The Avogadro's number, it represents the number of units in a mole. Now for mass. Okay, we talked about mass a little bit, we talked about molar mass. Now to go from mass to moles, what we do is we divide by the molar mass. So remember the molar mass, all those atomic masses from the periodic table added together, and we divide the mass that we're given by that number, and we get moles. To go the other way, from moles to mass, what we do is we multiply by. We go from moles to mass, we multiply by the molar mass. Okay? And it's important that you know how to do that. Okay, so you're given a number of moles, number of grams, a mass, okay, and you're asked to convert from one to the other. If you're given mass and you're asked for moles, we divide by the molar mass. If we're given moles and we're asked for mass, we multiply by the molar mass. Now, that is converting from mass to moles or atoms to moles. The other thing that we can ask is convert from mass to atoms. Okay, we just follow this little chart. We go from mass to moles by dividing by the molar mass. And we go from moles to atoms by multiplying by Avogadro's number. Conversely, we can go from atoms to moles by dividing by Avogadro's number, and then from moles to mass by multiplying by the molar mass. Notice that the molar mass is always, or the moles is the stopping point. Okay, notice that we always go to moles as a stopping point. Now the other thing we talked about that was really important, we had some other things, you know, types of reactions, stuff like that. The other thing that was really important was stoichiometry, that really scary word. And all we're talking about with stoichiometry is converting from mass of one thing to mass of another. Okay? You can also convert atoms of one thing to atoms of another, but what I'm really worried about is you converting mass of one thing to mass of another. Usually the mass of a reactant to the mass of a product. Now we drew a bubble chart for converting moles to mass and moles to atoms and whatever. I'm going to do the same thing for stoichiometry. Now usually in stoichiometry we start out with a mass of something. Okay, so the mass of A is what I'm going to say there. Now to go from mass of A to moles of A, we just said how to do that. To go from mass to moles, we said to divide by Avogadro's number. Okay, so from mass to moles, we divide, not by Avogadro's number, I apologize. It's very difficult to get everything right while talking to a camera, it's very weird. So to go from mass to moles, we divide by the molar mass. I can't tell you how odd it is to be teaching to a computer or to a camera. Okay, we used to the whole class and everything else get a little bit of interaction. It's very odd to teach to a camera. So, mass to moles. Okay, we can divide by the molar mass to get that moles. Now, the big thing with stoichiometry is called the molar ratio. Okay, the molar ratio. So what this is, if we're given what we want, we'll say B. We take the coefficient, that's what's written there, it's the coefficient of B over the coefficient of A. And this is from the balanced chemical equation. Okay, we're going to multiply there. So we've got the moles of A multiplied by the coefficient of B over the coefficient of A. And this is labeled as moles of A and moles of B. So our units still cancel. Remember, molar mass is grams per mole. Okay, so our mass will cancel, giving us moles. And we have moles of A under moles of B. So the moles will cancel. So now this gives us moles of B. Okay, moles of B. That's where we're at. And so remember, if we want to go to mass of B, mass of what we're asked for, what do? We multiply by the molar mass. Okay, so it's just the opposite of this. We divide it by the molar mass. We can multiply by the molar mass. Okay, and that gives us mass of B. This is a very important chart. If you can do this, then you have successfully completed Chapter 3. Okay? Other than some odd duck questions about atoms or moles or something like that, if you can convert from mass of A to mass of B, that's awesome. That is a majority of Chapter 3. Now, the last part of Chapter 3, we talk about limiting reagent, percent yield, and theoretical yield. Okay, theoretical yield is how much our limiting reagent would produce. Okay, and our limiting reagent is the reactant that limits the reaction from going forward and limits the amount of product that can be formed. So let's do an example. Very easy chemical reaction. 2H2 plus 1O2 makes 2 waters. Okay, so 2H2 plus O2 makes 2 waters. Now, here's a good question. Here's a common question that you're going to see. If we reacted 15 grams of hydrogen with, I don't know, 6 grams of oxygen, what's our limiting reagent? What's our theoretical yield? And if we produced 2 grams, what's our percent yield? Okay, so this is a really good question that I guarantee my class will see, and I can guarantee pretty much you'll always see no matter whose class you're in. Sorry, my screensaver went there. Now, so we've got a reaction here, and we say, okay, we'll react 15 grams of hydrogen with 6 grams of oxygen. How much water is produced? What's our theoretical yield? And what's our percent yield? Okay, and to do that, we have to find our limiting reagent. So we have to do all three. So to find our limiting reagent, the only thing we do is we do the stoichiometry problem. We do that stoic A to B thing that we just went over for both hydrogen and oxygen. Okay, and our B is going to be water for both. So we've got 15 grams of hydrogen. So it's mass of A, and we want to go to mass of B, which is water. Now, 15 grams of hydrogen. Molar mass is 2. And our stoichiometric ratio, for every 2 moles, our molar ratio, for every 2 moles of hydrogen we put in, we get 2 moles of water out. So it's 2 to 2, or 1 to 1 if you want to divide it out, but I'll leave it as 2 to 2. Now, like I said, don't worry if you can't see this. Okay, you can follow along and write it out. And our final step to convert to mass of B was to multiply. So now we've got moles of B. Our final step is to multiply by the molar mass of B, which is 18 for water. Okay, so we've got 15, which is our mass that we're given, divided by our molecular weight, or molar mass. And we've got our molar ratio, and then our molar mass for B. I'm going to grab my calculator right quick. Now, whenever we do this, we get 67.5 grams of water that can be formed. Let me do that again. I think I messed up on my calculation there. 15 times 18 divided by 2. Yeah, there we go. 135. Much better. So 135 grams of water could be formed. Now what that means, what that number 135 means, that means that if every bit of that 15 grams of hydrogen was used, we would get out 135 grams of water. So if we had all of the oxygen, an infinite amount of oxygen that we could ever use, in excess of oxygen, and we use 15 grams of hydrogen, we would get out 135 grams of water. Now, we're going to do this again for oxygen. Okay, so we've got 6 grams of oxygen starting out. Our molar mass of oxygen is 32. Our molar ratio, or stoichiometric ratio, for oxygen to water, for every 1 oxygen we put in, we get 2 moles of water out. And finally, we convert moles of water to mass of water. Now, it's not really necessary to convert all the way to mass, but I tell my class to do it because it makes the theoretical yield very easy, and in my test, I usually put the theoretical yield and limiting reagent together. Okay, so we got 6 grams of oxygen converted to moles by dividing by the molar mass. Then we have our molar ratio, and then multiply by our mass of B, which is water, so our molar mass of B. And so if we do this, we get 6 times 2 times 18 divided by 32. We get 6.75. So 6.75 grams of H2O. Now again, what that means is that if all 6 grams of oxygen is reacted, we would produce 6.75 grams of water. Now remember, if all of our hydrogen was reacted, we would produce 135 grams of water just looking at the hydrogen. And so you look at this and say, okay, if oxygen ran out, it would only produce 6.75 grams. Whereas if we reacted all 15 grams of hydrogen, we would produce 135 grams of water. And so obviously the oxygen is going to run out first, and we're going to produce 6.75 grams of water and have a whole lot of hydrogen left over. And then when we're asked for a theoretical yield, that's the beauty of doing it this way, is that when you're asked for a theoretical yield, you've already done it. It's right there. 6.75 grams of water, that's our theoretical yield. And so you do this, you do that chart thing that we just went over for stoichiometry, you do that chart thing for both reactants, and you find your limiting reactant, and you already have your theoretical yield done. Now finally for our percent yield, we take our 2 grams that we produced over the 6.75 grams that we should have produced and multiply it by 100. 2 divided by 6.75 times 100, and we get 30%. Okay, so our percent yield was pretty bad. It was only 30%. So that means that we produced 30% of the water that we should have, looking at our calculation of our theoretical yield. Okay. So that's it for chapter 3 review. That's the big things, the moles, stoichiometry, and then these last 3, theoretical, percent, and limiting reagent. Now in chapter 4, we're going to look at solutions first, and we're going to talk a lot about that. So we'll be looking ahead, look at the molarity equation, that's a big one. Look at acids and bases again. That's going to be nice because we get a review of our acid names, but you already know them. You already have the resources to go back and look at how to name acids. So I definitely recommend going back and doing that. Now, I'll post another one again for chapter 4 after on probably Thursday. I'll try to do it tomorrow, but probably not going to get around to it because I have a lot to do tomorrow. But I'll try to post another video for chapter 4 by Thursday night, if not Friday morning. And until then, study well, and I'll see you guys in class.